Alright, time for the draftphysics.com video presentation. So, I was working on another lever experiment, and, I accidentally kind of fell upon an idea, and it sort of worked, and it might be a shortcut. It might be a way of evading having to do the actual smashing things into things with levers, and instead just use a coupled oscillators, what they're called. So here's an example of the ones you'll find online. Now can't say for sure, okay, but I haven't been able to find any where they use uneven masses. So if somebody can find a coupled oscillator with uneven masses, like 2 to 1, ideally, that would be helpful.
Two masses.
So the idea is one stops. Okay, this one stopped now, and that one's got all the energy. Then this one stops. This one has all the energy. The energy is clearly moving back and forth, and the energy is momentum. The momentum moves from one object to the other object. The mass and velocity moves from one object to the other object. The fact is I accidentally it's really not an accident, I guess, because I thought of it. Why not use the lever to couple the oscillations? Because then I can have uneven masses without them knowing they're uneven masses. Okay, the lever makes them equal, and so it sort of did in fact work to couple the twice as heavy object to the other object, and to basically create a coupled oscillator, that is where all the motion is in one object and then all the motion moves to the other object. And that's basically all we want to do, is move the momentum from the heavy one and then move it to the light one, and then you move it back again, and you keep moving it back and forth. And as you keep moving it back and forth, it makes it obvious that there has to be the same amount of energy, because you're moving it back and forth, and it can go on for 15 minutes. So you're not losing very much of the energy as it cycles through. So there's no excuses about deformation or heat or air resistance or some other nonsense. It's clearly 100% of the momentum is in one object, and then 100% of the momentum is in the other object. And because of the mass differentials, it's clear, okay, that kinetic energy isn't playing a role anywhere. Alright, so with that stated, I guess it's worth drawing it, and then I'll link to a couple of videos that I'll leave as unlisted. So in the description I'll put a link to the 2 raw videos, and they're just raw videos. I can improve the experiment, but I really shouldn't have to because there should be a concession by... Maybe I can get physicist Michael to concede that if I can create a coupled oscillator between a twice as heavy object and a half as heavy object, that I will in fact be making it, it will not, it'll conserve momentum. And if he concedes it has to conserve momentum, then he has to concede that it won't conserve kinetic energy, and there'll be no evidence of kinetic energy. Alright, so what I have done is something rather simple. So I have a suspend from the ceiling. I have my balance, my lever, and I have merely hung from 7 or 8 feet on one mass. Well, this is the 2 mass side. 2 mass and a 1 mass. Okay, twice the distance. Alright, and basically how it works is, which is neat, you can actually get the motion towards each other. Now I have to do something to force them not to turn and to twist and to spin, so I can work that out. But so currently you just give this some motion, okay, force in, and what will happen is these 2 things will oscillate towards each other. And at one point this one will stop and all the energy will be over here, and then this one will stop and all the energy will be over here. And you can see quite obviously that this one's moving twice this fast It's doing a much bigger arc. The arc for this one is much bigger than the arc for this one. And conserving the momentum, and I would argue proving the point. Okay, now I didn't bother doing frame rates and all that crap because theoretically I shouldn't have to, because everybody should concede I can't change the amount of momentum. The same, if it jumps back, if it keeps doing this over and over again 10 times, 50 times, you'd have to concede that obviously it's all the momentum is going from one side to the other side. So it really is your job to say something else could possibly be happening. But anyway, we'll see. We'll see how reasonable people are, because this is a real concept. Everybody knows coupled oscillators. Physicists will concede momentum is conserved. So if coupled oscillators by definition conserve momentum, then this one has to be not conserving kinetic energy. And somehow you're ending up with more kinetic energy over here than you have over here. And that's nonsense. Everybody should know that can't be. I shouldn't have to explain why that would be ridiculous. All right. So let's find the two videos. And we'll do the forward back one, I think, first. I just have to find that one, which should be this video, I guess. I'm pretty sure. There you go, yeah. Alright, let's see how badly that looks. And such, we can get rid of the sound because there really isn't any. And, alright, so you can get the idea. Alright, the mirror screws it up a little. But this idea is, okay, so I gave the energy to the big one, and now it's transferring it to the small one in the background. Here's the small one, and it's getting faster, and its arc is getting bigger and bigger, and this one's slowing down and slowing down, and it'll eventually almost there, right about there, comes to a stop. And now all the energy is in the small one, and now it's going to start pushing on the big one. And it really looks, when you see it from different angles, it almost looks like they're magnets. And they're actually pushing on each other. It really has a real look of them directly interacting, even though obviously they're not directly interacting. So now we have a full swing over here, and this one, the little one is stopped. And now you're going to start pushing the little one again. So now for each swing, you can see the little one going faster, faster, and then it goes faster. And so the energy is being switched over to the other side and such. And it goes on and on. And this is a 15-minute video. So just one piece of energy put in, and this thing went on for 15 minutes. I mean, I'll just jump ahead. I mean, obviously it slows down, but I just mean 15 minutes later, it's doing the same thing. Well, in this case, 4 minutes. There's 7 minutes later. Yes, it's getting a little feeble now, but it's still doing the same thing. And, yeah, maybe it runs out in 10. Okay. I walked away. So I didn't watch the whole clip. But anyway, but they're still moving when I got back. That's the point. So obviously the energy of this experiment does stay in the experiment a long time. Alright, so now we'll find the other one. And see what we... So this is a better-ish angle. And, as I stated, imperfect. I should have made sure this one wasn't moving before I started. So there, I'm initiating the action. All right. So it's pushing on the little one, and with each movement, the little one's getting faster and faster. The big one's slowing down, and you can see the little one's going really quite fast. Very big arc. And there'll be a point where this one almost stops. It's going up and down, and that's what makes it look like it hasn't stopped, but it actually has stopped. And now the little one's going to push on the big one. So there, it pushed on it. And it pushes on it. And can you see that? Yeah. Yes, you can, even with me in the way. So it's pretty dramatic when you watch it. So now this little one stops. So it stopped, now it gets pushed. Push 1. Push 2. Push 3. And push 4. And so now it's really starting at 5. It's starting to speed up. 6. So the whole idea is instead of transferring the energy in a lever really quickly, you're doing it in little impulses. And obviously you're conserving an awful lot of energy. So the lever's moving up in the air, but it's moving up very little for the amount of action it's creating. So there's very little loss to moving the lever. So the lever is just doing a little movement, and it's creating the very large transfer of the energy from one side to the other side. So the little one is stopped. Now it's getting pushed again. You can just see it push, push. It goes faster and faster. And the arc gets bigger and bigger. So, in my opinion, this is good enough theory. Okay, now, like I said, we'll see if the buttheads are going to sit there and contest the function of a coupled oscillator and contest that momentum has to be conserved, and therefore contest that, yes, these type of experiments basically prove there's no room for two theories. There's only one theory. Either momentum is being transferred between the two objects or kinetic energy is. And the fact is that kinetic energy can't be, because obviously the two objects are different masses, and you can't conserve the momentum and the kinetic energy. It's not possible to conserve both. Alright. I don't know how much more you need to see, and blah, 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 blah. Like I said, see, I can probably run a wire that prevents them from turning, and so it'll be even more visually interesting because they'll stay pointed towards each other. And so that might make it easier not only to do frame rates if you feel it's necessary, or to by some other mechanism. You could always just measure the time of the period, I suppose. But anyway, we'll see. So maybe the lever experiment is unnecessary for the people who recognize that this probably has functionally duplicated the exact circumstance and done it in a way where I don't have to waste any energy moving a heavy lever. Alright. So the little one stops, big one's moving. Now the little one will start moving. The energy will go into its precession. Push. Push again. One more push. Two more pushes maybe. And then the big one will stop. And the little one has got all the energy. And then it'll go right back into the other side again. Alright. So maybe it's enough of a video. Let's see. See if we can get physicist Michael to respond to the concept of a coupled oscillator and the mathematical requirement that you basically have to conserve the momentum. And in doing so, you prove kinetic energy can't be playing a role. Alright. Probably enough. Yeah, wow, it's the end of the video. Alright, so like I said, I'll make the two videos available if you want to see them as links and such. in the description.